Welcome to the micro communication course. Today we will learn a directional coupler. So as we have seen that E plane T, H plane T and a magic T earlier, so for their ports we supposed to provide the input wave and we supposed to receive the output wave there. And then based on that we have obtained the scattering parameters or S matrix for the given T here. Now similarly we will learn here today that a directional coupler is nothing but one junction, and that junction will receive the power from the one source, or it will receive the power from the many sources there. And this device, if you see that it receives the power from particular point or particular input port here. If supposed to be this device is perfectly matched, then there won't be any reflection from that given port to all other ports there. Before proceeding with a coupler, so we should know that some requirement for the directional coupler. So in a directional coupler, we say that word is about a directional coupler. So in that case, so whichever the power input we are providing at any port, and then power will be received at the another port. Means we say that that is input to the output, whatever the power we are receiving, it has some particular specific direction there. Suppose we have a 4 port there, we have to apply the input to the one of the port. Then according to the direction of your guide, so power will be available there. Then when we consider that a power is given to the any other port, any one port, so that will be available into the another port. But some of the ports there won't be any output or there won't be any a power there. Or whichever the input signal we are providing to the any port, that will be divided to the any other port. Or we can say that if we are providing the input to the two port there, your power will be added or power will be divided there. So this one is about, we can say, a directional coupler. But when we talk about that addition of a power at a two particular port, so then we need to know about what will be the magnitude and phase of that particular signal. Now, how directional coupler looks like? Suppose we say that we have a 4 port directional coupler. Okay, so this one is about a directional coupler. So it has a port there. We say that a port one. Okay, so we supposed to be consider that port two, and this one is about a port three and a port. Okay, so for our simplicity, we say that one two. Okay, so that will be a port three and a port. When we provide the input to the port one, okay, I can say that we have incident at this particular port one, so then power output will be available at port one and a port three. Okay, we can say that for a given particular direction, when we consider that a input to the port one here, then power will be available at a port two and this particular port here. Okay, because in a given direction, your signal is to be propagating. So this is about an incident signal which is supposed to be considered at port one. Means we say that here input at a port one, input at a port one, so output will be available at port two and a port four, and no output at a port three. So any given direction, we supposed to say that this one is about the way your coupler is working. Okay, so we can say that this way in a given particular direction your coupler is working. We have the connection from port 1 to port 2, and then power coupling to the port 4. there is no coupling to the port. So why there is no coupling? Because this power will be cancelled at the port 3. That's why there is no coupling to the port 3 here. Means power incident or input to the port 1. So then their power will be coupled to the port 2 and port 4. No power coupling at the port 3 here. So in a given direction your power will be coupled there. Now another incident, if you say that, if we consider that input to the port 4, okay, I'm saying that input to the port 4, then what happened here? For the given particular directional coupler, input to the port 4, this one, so output will be available at a port 1 and a port 3, 1 and 3. No power output at a port here, port 2 here. Okay, so because we say that input at the port 4, output available at 1 and 3, no coupling to the port 2 here. Even if supposed to be consider that a input at a port 3 here, input at a port 3, output will be available at port 2 and a port 4, no coupling to the port 1. If consider that input at a port 2, no coupling at port 4 here, but power will be coupled at a port 1 and a port 3. Likewise, if you consider here, in this case here, power will be coupled at a given specific particular port here. One, okay, so likewise, in a given direction, your power will be coupled. So now from this, we need to calculate that what will be the coupling parameter. The coupling parameter, for that purpose, we should know that at what particular port we are going to provide the input signal there, and then we will get at what particular port we will get the output there. So according to that, we can find out the a coupling parameter for the direction coupler. So you remember that the port 1 here, okay, port 2, port 3 and the port. Now suppose we say that some of the port we say it is about the incident port with input, and then we are getting the output means coupling port. These are nothing but the coupling port. This one is about the incident port means input port here. Port 2 and port 4 in that case will be a coupling port, and port 3 no power will be coupled at this port 3. Okay. So now, so what is the coupling factor, or what will be the coupling coefficient? So in that case, we need to know about that what will be the incident power at this particular port 1, and what will be the power forwarded to the another port 4, because this one is about your main guide. And here a coupler means what we have a holes, multiple holes, or single holes, two holes, three holes, likewise. And this one is about the auxiliary guide. Okay. So in that case, the whichever the we have the auxiliary arm, so we are getting the output to the auxiliary arm, that is the port 4. Main waveguide is a 1 and 2 here. So another waveguide is likewise here, port 3 and port 4. And there is a coupling between this waveguide and this waveguide. So in between this, there will be a hole, one or two holes. Okay, likewise. So according to that, power will be coupled. So what will be the coupling power or a coupling efficiency? In that case, so this one is about the input signal or incident power at a port 1, and then power will be forwarded to this port 4. This one is about a main waveguide. Naturally, there is output, but what will be the couple at this port 4? That will give us the a coupling efficiency or a coupling factor. So we can write here a coupling coefficient, or we can say that a coupling factor. Okay, we can say that a coupling factor or a coupling coefficient C is equal to 10 log of whatever the input power and what will be the power forwarded to the port 4 here. That is a dB here. That is about a coupling factor. Okay, so we say that input 1 coupled to the port 4. Then a directivity. The case of a directivity, that is about the ratio of what a power coupled in the forward direction to the power coupled in the backward direction. So means where we say that incident is here port 1, power coupled in a forward direction, that is supposed to be port 4. Okay, this is about a forward direction. But if supposed to be any small power, small signal coupled to the port 3 here, okay, that is nothing but a backward direction. That is this one and to port 1 and a port 2 is a primary arm, primary waveguide, and this one is about a secondary arm. Okay, likewise, we can see. So, so now in that case, so directivity is equal to D is equal to 10 log of what will be the your forward wave, forward propagation signal, and a backward direction. That is about a pure. That is this one is about nothing but a ADB. Then a insertion loss. So insertion loss is nothing but what we are providing the power input to the port 1 incident signal at the port 1. Okay, see, and then what we can say that a power transmitted to the another port, that is about the main wall. So we say that from this a power incident to the port 1 and a power transmitted to the second, this one is about a port 2 here. Then it indicates the what will be the power we are providing to the one, okay, it's that particular number, and we are receiving the power at this particular port 2. So because of another arm or another secondary or another waveguide is present, so because of that there will be a small degradation in the power, because power will be coupled to the port 4 here. So that's why power will be reduced at a port 2. So that's why because of that insertion of another waveguide on another arm, then what will be the loss occur? So then we can say that a loss, insertion loss, is nothing but what? 10 log of, that is a P2 by P1. That is in a T. Next is about a isolation. Isolation means what? So we supposed to be consider that a port 1 is the input here, port 1 is the input here, and this coupler is a directional coupler, so forward directional coupler in this given direction. If input is at port 1, means incident wave is at port 1, so output will be available at port 2 and port 4 here. So this one there is no coupling. Okay, so means this port 1 and a port 3 are isolated here. Port 1 and a port 3 are isolated there. So what will be the isolation between that port 1 and a port 3? If supposed to be power incident at a port 1, so what will be the power available at a port 3? That is nothing but the isolation. So isolation is nothing but what is equal to 10 log of 10 log of P1 by P3. That is in a TB. That is about a isolation. Now this one is about a coupling parameters of a waveguide. Now we will calculate that, or we will find out what will be the S matrix for this directional coupler or a scattering matrix. So scattering matrix, we say that it has a 4 ports now. So scattering matrix for this coupler will be of a 4 by 4 order. So 1, S1 2, S1 3, 1 4, 2 1, 2 2, 2 3, 4. Then S3 1, S3 2, S3 3, S3 4 here, S4 1, S4 2, S4 3, S4. Now the order of the matrix is a 4 by 4. Okay, so we are getting the S matrix for the given directional coupler, and we say that this one is about a port 1, 2, sorry, this one is 3, this one 2, and this one is about a 4 here. So now what are those components here? Okay, so in general what we can say that when ports are terminated, when ports are terminated with a matched load, there won't be any reflection. Okay, so we say that if all these ports are match terminated, or we can say that all ports are matched, then that case matching condition that is port 1, port 2, port 3, port 4, there is no reflection occur at that given particular port. That's why these factors S11, S22, S33 and S44 becomes 0. That is a matching condition. S11, S22, S33, S44 is equal to 0. That is for the matching condition. Then another case, matching condition we say here, we'll write here, even you can write S11 is equal to S22 is equal to S33 is equal to S44 equal to 0. Then another is condition is what? There is no coupling. There is no coupling to the adjacent port here. Means what? When we say that a port 1 is the incident one, no power coupled to the port 3. Means port 1 and a port 3 are isolated here. Okay, so what we can say here, so if we are providing the input to the port 1 here, no output at a port 3, it will be 0. Or if we are providing the input to the, what you can say that, this one is again isolated, port 2 and port 4. Means if we are providing the input to the port 3, no output will be available at port 1, forward coupler. So in that case, S13 is equal to 0. So similarly, we can say that S24 is equal to 0, S42 is equal to 0. Okay. So why it is 0? If we are providing the input to the 1, this one is isolated, no coupling, only output available at 2 and 4. If we are providing the input to the 3, no output coupled to the port 1, output available at port 2 and port 4. If we are providing the input to the port 2, power will be forwarded in 1 and 3, no coupling at a port 4. If we are providing the input to the port 4, power will be coupled to the 1 and 3, no coupling to the port 2. That's why S24 or S42, S13 or S31 becomes a 0. So now we can write here again. Here we can say that S13, S31. Similarly, we say that S24 is equal to S42 is equal to 0. Now from this, we write here S13 or S31 0. This one is 0 here. S42, S24 is 0. So now if you obtain the S matrix again, if you rewrite for the directional coupler, okay, with this value, so what we are getting? Okay, I'll write here the S matrix again. That case, we have only the what we have. This one is a 0, only 0, S12, then 0, 1. Okay, S11, 0, S12, 0, S1. Okay, next we say that S21, 0, S23. Alternate terms are 0. S31, this one is 0 here, S32, then 0, S3. Okay, then F41, 0, S43, 0. Each rows and column, if you say that alternate terms are 0. Now say that here, alternate in two terms. Because there is condition for what? No coupling, these ports are isolated. And another condition is what? That we can say that we have the given particular port are matched. There are various types of a directional coupler. So the directional coupler, as I told you earlier, wherever we have a main arm, and to the main arm, we supposed to be consider there will be a lot of coupling component. Now, from that we say that coupling will be takes place between the main arm if it has a two holes are there. Okay, so in that case we say that it is about a two hole directional coupling. If it has a 4 hole there, then it is called as a 4 hole directional coupler. Or we can say that another one, Bethe-hole directional coupler. So it has a single hole. Okay, we can say that if it is about a reverse coupling, then we can say that it is about a Schwinger coupler. So now simple, if you consider the 2 hole directional coupler, we're supposed to say that this one is about your main waveguide. Okay, so here we're supposed to now this one is about a 2 hole directional coupler. So there are the 2 holes, 1 and 2. So that's why it's called as a 2 hole directional coupler. This one is about your main waveguide. This one is about a secondary guide, main waveguide here, coupling power through this main waveguide, and this one is about a secondary one. One main one, this one is a secondary one. Okay, right. So we have the power coupling through this given port. This one is the opening here. So power will be coupled inside this particular guide. Okay, so inside here through this 2 holes here. Now port 1 and port 2 we say here earlier 1, 2, 4 and 3. There will be when incident power at a port 1, power will be coupled at a 2 and 4. Means you can say that in a given direction your signal is propagating. Okay, this one is about a given direction your signal is coupling. Likewise. Okay, but what happened here when it reaches to the port 3? So it will be here this one and through this again come here. There will be cancellation takes place, which we say that at this port 4, at this particular port 3, so power will be cancelled out. Okay, at this particular port, so power will be cancelled out. Now we find out here. So what will be the coupling factor? Okay, so our aim is about to find out what will be the coupling takes place at the given particular port. So we're supposed to be find out here at a particular port. So that coupling is depending upon that what will be the holes here, size of the holes here, and what will be the spacing between these two particular holes. According to that, a power will be coupled at a given particular port that will be maximum or a minimum. So we need to know about what will be the spacing between these two holes here. So that 2 hole spacing is equal to L is equal to twice n plus 1 into lambda g by. So it is depending upon that what will be the guide wavelength. Okay, so that spacing between these 2 holes, it will be depending upon that what will be the guide wavelength there. And if we consider supposed to be these holes are not perfectly at the specific guide wavelength, so then coupling will be whatever the power will be coupled at given particular port that will be reduced here. So there are the another coupler we say a 4 hole coupler with a hole directional coupler. So again they have the same ways according to that how many number of holes. So that according to that they have the power coupling takes place there. Next we will see that a another component that is about a isolator. So now in a isolator, so what happened here in the isolator? So isolator forward the signal in one direction, and it will not allow the signal in the backward direction. So we say that isolator is a, what we can say, that a forward coupler. We supposed to say that it will be a forward coupler. If only given particular direction, your power will be coupled, and in another direction, your power will not be coupled inside the through this isolator. So how it will be? We supposed to be consider that how it happened here. So for a given particular waveguide, inside a particular waveguide, so we need to consider a ferrite material. Now the ferrite material, it is a, that material has a property when your microwave signals, okay, when your microwave signals will be passed through this ferrite material, so then that signal will rotate. Okay, so means what we can say that here we have the supposed to be a signal is likewise, it is propagating through the ferrite rod here. So then signal rotation takes place. It will be 45 degree, it will be 90 degree, it will be 180 degree, likewise. Okay, so that's why it is called as a Faraday rotation. So that Faraday rotation, it is depending upon that a microwave frequency. If the microwave frequency is greater than the wobbling frequency of this particular ferrite here, so then and then there will be a change in the polarization of a wavefront, or you can say that we can say that there will be variation in the or that particular signal there. So polarization of the signal will be changes here. So suppose we say that for a given particular waveguide, if whether it will be a circular or a rectangular one, if supposed to be there is a ferrite rod is present. So now if supposed to be we say that a direction of a signal is likewise at this particular place here. So when it reaches at this particular point, your direction of the signal will be changes because of that, whether it can be a 45 degree or 90 degree. Okay. So based on this ferrite material, according to the ferrite material, so polarization of entering wave, okay, here we can say that it will be entered here, and at this particular place, so that polarization of a leaving wave will be changed. So now that particular principle is used in a Faraday rotation. Now aim is here entering wave, then we are saying supposed to be leaving wave here. Okay, so now there will be change in a phase that is about a 45 degree. So in an isolator, the same principle is used so that only your wave is propagating through this isolator only in one direction. Okay, so for a given particular two-port network, so we say that it is just like a two-port network. It has the two ports there. So if you could find out the matrix here, so it will be S21, S22. So now since these are the port match, so this will be 0. So only if we say that the input is a 1, port 1, so output will be available at port 2. Okay, so we say that input is at 1, output will be available at port 2. So in that case, what will happen? What we can write here? So this becomes isolator S matrix becomes what? 0, 0, and 0. That is about the isolator matrix. Isolator scattering matrix. So only one direction it allows the power to be propagating in a one direction, and there is no transmission takes place in another direction. Okay, so device that is about a isolator, port 1 here, and this one is about a port 2 here. It propagates the power in only one direction. There is no coupling to the power at the port 2. So only if supposed to be provided if input at port 1, power will be available at port 2, If we are providing the input to the port 2, power will not be available at a port 1. Okay, so only in one direction power will be coupled. How your circuit, how your exactly wave that isolator component is there. Now see here, there are the sections of a ferrite material or a ferrite sheet, and through this section, so we supposed to be get that. Okay, so there will be a twist or there will be a variation in the what we can say that because of that ferrite material, there will be a rotation of your signal takes place. So now we will see that how that rotation is takes place here through this guide. Now we supposed to be, so now here is a small section. Okay, so you can say that there is a small section of a guide is present here. Okay, so here, a minute. This one is about a ferrite section here. This one is about here. We have the ferrite rod, the sheet. Okay, so this one is about a ferrite rod here. The ferrite rod, it is inserted along the axis of a rectangular waveguide, and there are the two attenuator. Okay, or we can say that a sheet or a resistive card that are placed at the input side and a output side of a guide here. Now, if we provide the input to this port here, port 1, okay, if we are providing the input to the port 1, so what happen? Our signal will be likewise. Okay, so that we can say that, so at this particular point, our signal will be likewise. Okay, so that's about our view here. Now that at each and every section, so this is about A, and at this particular sheet, our wave will be likewise here, and then because of a ferrite rod, there what will happen because of that ferrite rod, your waveguide, that whatever the wave is propagating there, that will be rotating in a clockwise direction. And a rectangular waveguide is about a 45-degree twist, and because of a twist, okay, because of this particular twist, this one is about a guide. We supposed to be consider. So it will be twisted 45 degree. Okay, so this will be twisted by 45 degree. So suppose we are expecting that your signal will be twisted 45 degree because of a twist. And then when it pass through the ferrite rod, then again it will retain whichever the 45 degree is there. It will retain. And then so as it is at this particular when at this particular sheet, it is be propagating here, and then we'll get the same signal at this particular point. So there is a sheet, there is a twist, there is a ferrite rod. If that, what is the role of this particular ferrite rod? It will twist a signal by 45 degree. Okay, that it will rotate your wave 45 degree, and this twist will rotate your signal in a 45 degree. And the role of this resistive card, that resistive card will absorb whichever the signal, those having the plane of polarization parallel to the plane with the resistive card. So, so here at this particular input side, it will be perpendicular. So that's why that signal will not be absorbed here. Even if you say here, it will be perpendicular. So signal will not be absorbed. So what happened here? So perpendicular to the resistive card, then 45-degree twist, and then retain again a 45-degree, then it will be perpendicular again here. So that's why your wave will be likewise. But if you consider that in another way, if we provide the input to the port 2 here through this, signal will be perpendicular initially, then it will be twist 45-degree. Okay, so 45-degree early twist now. So then I supposed to withdraw here. Signal likewise, we say your signal will be twisted by this ferrite rod, 45 degrees. Then when it reaches to the again twist here, again it will be likewise. Okay, so means it will be twisted again a 45 degree. Okay, so what we can say here, it will be twisted likewise. So 45-degree and a 45-degree. So and at this particular here, okay, so then what happened here? So it will be parallel to this registry card. So because of that parallel to the registry card, so that registry card will absorb all the power, all the signal that will be propagating through the isolator. So that's why here we say that a port 1 and a port 2, if we provide the input to the port 1, so output will be available at port 2. If we provide the input to the port 2, no output at a port 1. Okay, so no output. So that is about your S matrix of isolator. So if we provide the input to the port 1, output available at port 2. All other components are 0. That is about a isolator. Next, we supposed to be see that another component is about a circulator. So now in isolator we have seen that there is a ferrite material, and due to the ferrite material your signal gate rotated here, or rotation of a signal takes place in a isolator. Now the same principle is used in a circulator there. That ferrite rod is there, and that because of that ferrite rod a rotation is takes place. So immediate port there will be output, and other port there is no output. So circulator. So it's supposed to be considered there will be a n port circulator there. Now we'll take an example of a 4-port circulator. So in a 4-port circulator, we draw here port 1, okay, 3, a port. Okay. So now this one is about a direction. Here we say port 1, port 2, port 3, and port. Now in this case, what happened? So if we are providing the input to the port 1, output will be available at port 2. No output will be available at port 3 and port 4. No coupling to the port 3 and 4. If we are providing the input to the port 2, output will be available at port 3. No coupling at 1 and 4. If we are providing the input to the 3, coupling will be takes place at power will be available at port 4. No coupling at 1. If we are providing the input to the port 4, output will be available at port 1. No coupling to the port 2 and a port 3. Now if you obtain the S matrix for this circulator, so it is a 4-port S11, S12, S13, S21, S22, S23, S31, S33, S34, S41, S43, F44. Now in this case, if you see that what happened here, now for this, so given particular port, all these port matching condition, so this becomes a 0. Okay, we say that this becomes a 0. And we say that if we are providing the input to the port 1, okay, if we are providing the input to the port 1, output available at port 2, no coupling at a port 3 and a port 4. This one is equal to 4 is equal to 0. It's S31. Okay, so this one S310 and S410. If we are providing the input to the port 2, power is available at port 3, no coupling at port 4 and port 4. Is what? Input to the port 2, no coupling at port 4, input to the port 3, 2, no coupling at port 1. Okay, this becomes 0. Means S42. This one will be 0, S12 will be 0. Next, we say that if we are providing the input to the port 3, output available at port 4, no coupling at port 1 and a port 2. Then we say that put to the port 3, no coupling to the port 1, put to the port 3, no coupling to the port 2, that will be 0. S13, 0, S23, 0. Okay, so now next, if we provide the input to the port 4, power will be available at 1, no coupling to the port 2 and a port 3. Then we can write S41, no coupling to the 2, S4, no coupling to 3, that will be 0. S24 is 0, this one. S34 is 0, this one. So if you see that we have only what? Both input, one output, one input, two output, two input, three output, four input, three output. So that is about your, we can say here, the S matrix. Okay, so if we rewrite the S matrix for the circulator here, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0. This one is about a S matrix for the circulator. Okay, so now how it how it will be not allowing to propagate the signal to the other port, because inside that a ferrite rod is there or ferrite material is there, and due to that the signal is not able to propagate through the circulator there. Okay, so we'll see here. So yes, circulator here. We'll see here the circulator now. Okay, this one we can say here. We have the ferrite rod is present, so it will twist signal to the 45-degree here. 45-degree twist by this ferrite rod, and then we have the another port here. So this one is about a port 4, port 3, port 1, and a port. Okay, so this one we say that 1, port 1, port 2, port 3, and port 4. This only in a given direction your signal is propagating. We say here earlier 1, 2, 3, 4. Only this direction. Okay, so 1 to 2, 2 to 3, 3 to 4, 4 to 1. Other are no coupling. Okay, no coupling to the other port here. So that is about your circulator here. So, so thank you all of you. With this, we stop here. Okay. Thank you all of you.